In this video, we look at how do we implement the conventional AM. This video is based on the concept of overmodulation, which we talked about in previous video. This is how do we implement the conventional AM. We multiply 1 plus AMNT by the carrier. So this portion is the carrier, AC cosine 2 pi FCT, that's the carrier. And what is MNT? That's a normalized message signal, which is taken by MT divided by maximum absolute value in MT. And this is for OT. A is the modulation index. It's called modulation index, which will determine the portion of MNT goes into the magnitude of the carrier. And A is in between 0 and 1. If we look at this modulated signal of conventional AM, we can break it up. There are two terms here. One term is cosine 2 pi FCT multiplied by 1. The other term is EMT multiplied by cosine 2 pi FCT, right? So if we look at this portion is double sideband suppressed carrier, that's DSBSC signal. And this portion here, apparently that's carrier. Now we can see the conventional AM is no longer suppressed carrier, and carrier it is here. It is transmitted. The reason why do we want to transmit the carrier, because we want the whole signal, we want the conventional AM not overmodulated. We have to have 1 here, this portion 1. Now next look at how do we obtain this normalized message. I'm using an example here. Suppose MT, this is MT for this shape, any shape, I just made it up. The message is in between -4 and 1. So what is maximum value for absolute value of MT? That's 4. And that equals to MT divided by 4. So first, everything is scaled by 4. So -4 becomes -1, and here 1 becomes a quarter. So this is MNT. Now let's look at if I have A equals to half. If A equals to half, everything scaled by half again. So a quarter becomes 1/8, -1 becomes -half. But signal shape does not change. What about 1 plus AMT? The value of this function is added by 1. You can see here -half become half, and 1/8, that becomes 9 divided by 8. And the shape of the message is still remain the same. So this portion is going to be multiplied by the carrier. What we can observe here, 1 plus EMT, this portion, always greater than 0. So therefore, overmodulation does not happen for the conventional AM at all. And that satisfies the design criteria for conventional AM. Next, let's look at the spectrum of the conventional AM signals. Spectrum is very important in communication systems because spectrum will determine the bandwidth for the message signal being transmitted on the channel. The smaller the bandwidth to transmit a signal, the better. Because imagine if I have a limited bandwidth for a channel, for example, from 1 gigahertz to 2 gigahertz. If I transmit each signal using smaller bandwidth, I can transmit more signals within the same bandwidth I have. Now let's take the Fourier transform of the modulated signal. So U of f, we take the Fourier transform of U of t, and using the linearity of the Fourier transform, there are two terms here, linear combination. We take the Fourier transform for each waveform and then sum them together. Let's look at the second term first. That's AC, and small a has a modulation index, MNT, time domain signal, cosine 2 pi FCT. this term, 1 and cosine 2 pi of ct. You take Fourier transform. The Fourier transform of the first term, this term, and notice this is a scalar. We take it out first, and then we use modulation property on these two terms. MNT cosine 2 pi of ct. We have this MNT, Fourier transform M and F. So the Fourier transform of M and T, normalized message, if we take Fourier transform of that, we call it M and F. The spectrum move to FC and minus FC, you take half. So this is a modulation property. This is the same result from the DSBSC. What about this one? This is a two-delta function at FC and minus FC because this is cosine signal. M and F, that equals the scaled of MF because this is a scalar. It's a number. So assume that MT, that's MF. So we scale the Fourier transform of the message by this quantity. That will equals to M and F. Apparently, it is a scaled version of MF. To illustrate this in a simple example here, suppose I have MF this shape. Triangular just make it easier for me to draw. Then what is M and F? The same shape but scaled. Then what is U of F for the conventional EM? And M and F move to FC and minus FC, you scaled by half small a and big AC. Do this. Half small a and big AC. This portion move to FC. And this portion, same portion, and this portion move to minus FC. That's here. This and here. And then plus this. That's the delta function sitting at FC. The magnitude AC divided by 2. Same thing here. So you can see from the spectrum, the carrier is transmitted here. What's the bandwidth in the modulated signal? You can see here. This is the bandwidth from here to here. It's 2W. The modulation index is less than 1. The value of A controls the fraction of the normalized message goes into the carrier. For example, if A equals to half, which means that 50% of M and T will be introduced into the magnitude of the carrier. In other words, carrier amplitude will vary by 50% of MAT above and below the original value of this carrier magnitude. If A equals to 1, the carrier magnitude will vary by 100% of M and T above or below the original value of the carrier magnitude.